Before we begin, we'd like to thank the National Science Foundation Office of Polar Programs for their financial support to ARCUS and this seminar series. Now I'd like to introduce our speaker. Dr. Jessica Mejia is an assistant professor of cryosphere and polar sciences in the Department of Earth and Environmental Sciences at Syracuse University. Syracuse University is a new ARCUS institutional member. Thank you for joining. Dr. Mejia is a glaciologist whose research focuses on understanding how water interacts with glaciers and ice sheets to affect ice flow, the understanding of which is important to constrain glacial contributions to sea level rise. She uses observational field-based methods, hydrologic, geodetic, and geophysical process-based models, and remote sensing to study the structure and evolution of the glacial hydraulic system and the physical processes controlling the hydrodynamic coupling on the Greenland ice sheet. Other interests include working towards efforts to increase diversity and build community within the cryospheric sciences. Welcome, Jessica, and at this point, I'm going to turn the seminar over to you.
Thank you. Let me share my screen. Can you see it okay?
Perfect.
Great. Hi, everyone, and thank you, Janet, for that wonderful introduction. Yeah, my name is Jessica Mejia. I am very excited to speak to everybody today and tell you a little bit about my research studying the glacial hydraulic system. And today I'll be focusing on some of my research in Greenland. Before I get started, I wanted to say that, right now I'm a new assistant professor at Syracuse University in central New York or upstate New York. It's on the Onondaga Nation and firekeepers of the Haudenosaunee and indigenous people who ancestral land Syracuse University now stands, and with the Onondaga Nation and the Oneida Nations are our current neighbors. And there are a lot of collaborations with those communities at Syracuse. So this little arrow just points to where Syracuse is, and I know we're quite far removed from the Arctic. But I want to give a little introduction to some research going on here at Syracuse in the Department of Earth and Environmental Sciences, done by myself and my colleagues. So my colleague, Melissa Chipman, she is an assistant professor as well, and she is a paleoecologist and paleoclimatologist doing a lot of work all over the Arctic. This little map up in the corner shows where some of our research locations are in field collections. Melissa does research in Alaska, in the North Slope, Central Alaska in the Boreal Forest, and then also in parts of Southwest Greenland, mostly collecting sediment from lake cores and then doing analyses here in our lab to collect leaf waxes, evidence of boreal fire, and reconstruct those histories. She is also an affiliate with the Syracuse University Center for Global Indigenous Cultures and Environmental Justice here at Syracuse, which is a newer program. It's been here longer than I have, but so she's an affiliate member of that and doing a lot of great work there. Professor Aaron Mohammed, he is also an assistant professor, and he is a hydrogeologist doing a lot of work up near Tulloch Field Station in the North Slope. He is studying permafrost hydrology and does field work there, and then a lot of modeling work to supplement that. And I think he was just in Alaska this summer as well. And then me, I mostly have recently studied Greenland, but I've also worked during my master's degree at the University of Alaska Fairbanks. I studied a small glacier, Yahtzee Glacier in Alaska. So yeah, that's just an introduction to our department. We're very excited to be new institutional members and work with ARCUS and meet everyone. So diving into my research, my research has recently focused on Greenland, and a lot of the motivation for this is that the mass loss of the Greenland ice sheet has been accelerating. So here is a photo of Greenland and overlaid by some ice velocity flow lines, and the colors show where mass loss is concentrated. This graph is going over time and just showing that we are constantly losing mass from the Greenland ice sheet, and that's been accelerating since the 1990s. Currently, mass loss from the Greenland ice sheet is one of the biggest contributors, and if not the biggest contributor, to global sea level rise now, and it will continue to lose mass throughout the century, regardless of any climate mitigation strategies that we implement. But the magnitude of that mass loss is a big consideration there and is very dependent on our future climate emission scenarios. So just to provide some background information, so here if we kind of slice the ice sheet from the middle outwards, here's a diagram of that. On the right-hand side, we have a lot of snowfall, and this is where we're going to have mass gain on the ice sheet's interior. Then lower on the ice sheet, at lower elevations near the coast, we have the ablation area where you'll have bare ice in the summer that then melts, and we are losing mass. Mass loss occurs in two primary ways, which is the melting and runoff. So the melting of that ice, liquid water that eventually will be routed into the oceans. And then ice dynamic calving. So as the ice is sliding towards the oceans, we're breaking off chunks of ice into the ocean and creating icebergs, which like those which sunk the Titanic. While these two processes are often treated separately, they're actually interconnected. So when water produced on the surface of the ice sheet reaches the base, it actually creates a lubrication effect that makes the ice slide faster towards the oceans, can increase this ice dynamic discharge eventually, because the ice is actually moving down slope more quickly. And importantly, this process isn't really captured by current models that are creating our larger projections of future Greenland ice sheet or ice sheet mass loss. Just to break down and give an overview of the glacial hydraulic system, we have the supraglacial, inglacial, and subglacial drainage system. So the surface, inside the glacier, and then underneath the glacier. Those three components of the drainage system. On the surface of the ice sheet, meltwater produced will form superglacial rivers and streams that will route this meltwater across the surface of the ice sheet, mostly downslope. It can collect in lakes, forming superglacial lakes, or it can be routed until it finds a crevasse and forms a moulin. A crevasse is a crack in the surface of the ice that is created whenever the ice is just fracturing at the surface because of the ice motion and ice dynamics. When meltwater, like in a stream, reaches a crevasse, it will fill that crevasse. And because the pressure gradients at the tip of that crack are so high and the density of water is higher than that of ice, this fracture can propagate deeper and deeper if we keep on supplying enough meltwater to that crack, and it can eventually reach the base of the ice sheet or a glacier, which in the case of the Greenland ice sheet can be half a kilometer up to a kilometer thick. And we are hydrofracturing and creating these surface to bed connections. Once you create one of these surface to bed connections and you keep on supplying meltwater to this crack, it will form what's called a moulin. And in this whole process, this is watering, exiting the superglacial drainage system and going inside of the glacier itself. So here's some photo of a moulin, what it looks like from the ice surface on the ground. Here you can see some superglacial streams just disappearing into these holes. This is a moulin called Phobos Moulin, we named in Greenland, in Western Greenland. And this photo was taken in 2018 during the melt season. So you can see all that meltwater that was recently produced, and it's currently flowing into that moulin and reaching the bed. So it's creating this whole hydraulic connection. Whenever we returned to this location after the melt season had ended and there was no more surface melting, my colleagues repelled into this crevasse, and this is shown in this photo here on the right. So this is what just like that very upper level of that moulin looks like. And all of this used to be a narrow crevasse that was then fractured all the way to the bed, and all this water flowing very violently into this crack melted out this very large cavernous space. Once water gets underneath the glacier, it enters the subglacial drainage system, and this is composed of subglacial channels. On the right, we have a picture of what one of these looks like, and in some areas you can walk right into them. Many of them are in Alaska or smaller glaciers you can walk right into. And water that's produced, these are connected to moulins, and water will quickly be transported through these things. The other part of the subglacial drainage system is called the distributed or linked cavity system, which is just a very inefficient drainage system where water is slowly moving, much slower than in these channels that really you can think of as pipes that are just quickly routing water from the moulin downstream. So hydrodynamic coupling, how this is all working is that whenever you have a lot of meltwater inputs to a moulin or they've reached the bed, we can pressurize the bed, and all this water gets ejected over a large area, and we speed up the ice. And then as the subglacial drainage system evolves in response to all that meltwater, such as that conduit enlarging and growing over time by melting of all that water, it can then drain a lot of water from the bed, and it can slow sliding speeds. So there's this relationship between meltwater inputs and the structure and the evolution and the change of the subglacial drainage system. And that is what's really governing how much lubrication is happening and how quickly the ice is sliding down slope towards the ocean or downstream. And to understand how the Greenland ice sheet will respond to future warming, here is a figure from the IPCC's AR5 report, so the Intergovernmental Panel on Climate Change. And here we've been collecting observations of mass loss, and we've had ice sheet models for long enough that we can now compare how our projections match observations. And in this comparison, we've seen that we consistently, our mass loss for global glaciers or ice sheets is tracking the upper end level of our projections. On the right-hand side, you can see some of these future projections from 2040 to 2100, and the ranges that are indicated are the error bars. So there's still a lot of uncertainty in these projections. And one of the things that we need to do in order to constrain these projections, and particularly these upper level projections, is to understand the physical processes that are governing hydrology and ice dynamics and how that's evolving over time, and how those relationships will change in response to continued warming in the future. So that's a lot of the motivation for my research, is to understand some of these physical processes. And because of the Greenland ice sheet and how quickly it's changing and how melting is now affecting it, that's a great place to study these processes. So first, I'm going to talk about some of my work on Helheim Glacier and the drainage of firn aquifers. This work was funded by the Heising-Simons Foundation with a lot of amazing collaborators at the University of Buffalo, Kristen Poinard, Dartmouth, Colin Meyer, and Aaliyah Summers, and the Georgia Institute of Technology, Winnie Chu. And we've had some great graduate students and mountain guides who have come out to the Greenland Ice Sheet with us on Helheim. So a lot of work has gone in by a lot of other people has gone into this. So back to this diagram that I showed earlier, where we have the accumulation area where we're gaining mass and we have a lot more snowfall than we have melt, and we're always seeing snow at the ice surface versus the ablation area where it's ice-free. In the ablation area, right, we have melting that happens on the surface, and then it can flow through supraglacial streams and rivers over the ice, and it can collect. In the accumulation area, however, we're not forming these supraglacial streams. So I'm going to zoom into this area where, one, we do have melting, but it's not on bare ice. We're having melting of the surface snow or firn, which is just old snow. So here's a diagram zooming in, but so whenever we have melting on snow, this water will melt and then it will percolate vertically downwards, right? This is instead of flowing over the ice surface, it will flow vertically through the firn. And here's a photo from Greenland just showing what some of these melt layers in the firn look like. This water will continue to percolate down and in some instances can collect in something called a firn aquifer. A firn aquifer is where all of this water percolates down as much as it can, and then it hits a thermal boundary where it will refreeze below that point. So instead of moving further, it collects in an aquifer and then it will float down slope from there. Here, this figure shows is from Mejia et al. In 2016, showing the firn aquifer distribution in Greenland. So you can see here, firn aquifers are indicated by any of the colored dots, and they're concentrated mostly in the northwest and in the southeast Greenland. And this is because you need two things to form a firn aquifer. First is you need a lot of melt so that enough water melting is being produced and enough meltwater is being produced that you can actually form a very large melt layer. But you also need a lot of snowfall, because once you get a lot of snowfall quickly, it will actually create an insulation layer at the surface, so that water that was melted and percolated down over the course of the melt season, so it doesn't refreeze. Because otherwise it would refreeze and become a big ice lens within the firn. But whenever you have enough snowfall that falls quite quickly, then it insulates that and allows this liquid water to persist for well over a year, multiple years, even tens of years. The length of time is debated, but for quite a while, interannually for sure. So this work focuses on Helheim Glacier, which is located right here, where you see this big concentration of firn aquifer detections. So the firn aquifer is indicated in this figure by this pink shading on Helheim. Ice is flowing to the right in this photo. And what has been identified via satellite imagery is the presence of these very large crevasse fields and wide crevasses that are downstream and bounding the firn aquifer on the downstream side. So water within this firn aquifer is flowing from the left-hand side to the right-hand side. And here is a photo, or I mean a video of what this large crevasse field looks like. So you see these very wide crevasses, and that's presumably draining the firn aquifer. Why this is important is because if water from the firn aquifer is draining through crevasses and reaching the base of the ice sheet to lubricate the bed, this is the upstream most point where we're getting a direct surface to bed connection. So if, say, firn aquifer water was not reaching the bed, there was not flowing into crevasses that can hydrofracture or anything, that would mean that any of the melt produced would just be stored on the surface of the glacier. So that wouldn't contribute liquid water to sea level rise, because it would just eventually refreeze, and it wouldn't affect the structure of the subglacial drainage system or how quickly the ice is flowing over that area. So the blue bar here shows where we know meltwater is reaching the bed in the ablation area, but we can extend this area quite a bit further, tens of kilometers further, with these firn aquifers draining. So previous work by Chris and Poinar at the University of Buffalo, some preliminary modeling work showed that it is possible for firn aquifer water to drain into crevasses, hydrofracture to the bed. But this process and the timescales involved and the controls on these processes were very poorly understood because of the few few direct observations of the process or of the firn aquifer itself happening. And again, this is important because it could precondition the subglacial drainage system to influence these downstream sliding speeds. So today I'll talk about some work that answers these questions. One, where is the formation of region of the crevasses that drain the firn aquifer? And to assess if this boundary can potentially move inland in response to climate change. In this main picture right here, I think you can see my mouse. Again, we have that pink shading showing the firn aquifer, and all of those different colored dots are the actual firn aquifer detections that shaded region is based upon. So this work concentrates on the southern branch of Helheim Glacier, where this star is right where there are these consecutive observations of firn aquifer or consecutive firn aquifer detections by the Operation Ice Bridge campaign, which flew a radar all over Greenland. And with that data set, the elevation of the firn aquifer and the depth beneath the surface was detected, and that's how the distribution of aquifers were detected as well. So from that star, we have a zoom in of the study area here. Ice is flowing from the left to the right, and then water within the aquifer that's beneath the snow surface, so you can't see it on the surface, is also flowing from the left to the right. And the shaded area is that crevasse field with these large crevasses that are actively growing over time that we can identify through satellite imagery. In 2023, we installed several GPS stations on the ice. So those are indicated by these orange dots, and they were deployed in a strain diamond configuration so that we could measure how much the ice is pulling apart or compressing together spatially and over time. Up in the left-hand corner is a view of one of our central GPS stations, and this just flat ice topography. And then our downstream-most GPS stations in the crevasse field were actually deployed on either side of a crevasse suspected of actively hydrofracturing to the bed. And you can see, if you look closely, the two GPS stations right here on either side of this crevasse. So to answer the first question, where is the formation region of the crevasses draining the firn aquifer? Reviewing satellite imagery, for example, where there are these black dashed lines, we can identify these very narrow crevasses, and they're located approximately 1.5 kilometers away from the area where we see these large, wide crevasses, like pictured on the left, that are growing over time and indicating that we are actively hydrofracturing or had hydrofracture to the bed. Because the ice is flowing at about 200 meters a year, it would take a crevasse, one of these narrow crevasses, over 5 years for it to advect all the way downstream to the location where we're seeing these crevasses actively opening. So are the crevasses forming upstream in this area where we have these dots and then advecting downstream and eventually, for some reason, hydrofracturing to the bed, and it takes maybe 5 years for this process to occur? Or is something different between these crevasses formed at two locations if it does not take over 5 years? So to investigate this, I used a crevasse propagation model that I wrote in Python, and it's open source, available to anyone else to use, that considers all the processes involved in the slow fracture propagation, as would be the case for an aquifer. So I used this model with satellite imagery to investigate how long hydrofracture is taking. So here on the right-hand side, we have the crevasse that we have those GPS stations around, and the other slide that I showed. The first instance of this crevasse being observed in satellite imagery, which is sporadic, but it's from April 21st, 2022, at which time it was approximately 2.3 meters wide. So running the crevasse propagation model with parameters selected for our study site on Helheim Glacier, the model shows that it takes about 40 days for the crevasse to begin the hydrofracturing process and reach a width of 2.3, 2.4 meters wide. So this indicates that in this photo, when the satellite imagery was collected, the crevasse was around 40 days old. Unfortunately, we don't have another image of the area until the next year, March 28th of 2023, where the crevasse was 8.5 meters wide. Continuing running our crevasse propagation model for the area, it shows that when the crevasse was 6 meters wide, so before this 8.5 meters, the hydrofracture should have already occurred. So these results are saying that it takes less than a year for the entire firn aquifer fed hydrofracture process to begin in our area. So what that means is that these narrow crevasses here outlined in blue or delineated in blue, they are not slowly evecting or slowly hydrofracturing over half a decade. Instead, there's something different about the crevasses that stay narrow and are more upstream than the crevasses that are actually draining the firn aquifer and widening pretty quickly over time. After understanding that this process takes less than a year, that I was curious as to why some crevasses are draining the firn aquifer and others aren't. And to understand that and to understand if this drainage region of the firn aquifer can move inland over time, because if crevasses are there, I decided to use a similar model, to investigate the reasons for each of the crevasses that we see and why some are draining the aquifer and why some are not. So looking at the same study area, here is just a little overview of the same map figure up in the upper left-hand side. And zooming into this flight line of the Operation Ice Bridge for an aquifer detections, here I'm zooming out over the entire flight line where we are detecting the firn aquifer. So where you see these white lines, that's where there's that active crevasse opening, and that cluster of orange dots is where we have those GPS stations around that hydrofracturing crevasse. And then the flight lines move upstream for about 40 kilometers. On the bottom panel, those are the actual firn aquifer depths beneath the ice surface, plotted for different years from 2010 to 2017. And all this data was produced by Mejia et al. From those Operation Ice Bridge radargrams. And the crevasse opening area is shaded right here in that purple color. So I wanted to assess if, again, this downstream firn aquifer boundary could potentially migrate inland over time. And what are the controls on that? So to understand if this can change, I use a linear elastic fracture mechanics model. So what this will do is that you can calculate the initial depth of a crevasse. And I postulated that the difference between a crevasse draining the firn aquifer and one that isn't is that some can reach water from that firn aquifer and others cannot. So using a linear elastic fracture mechanics, right, we can use the background stress field. So how strong is the force of the glacier pulling the ice apart to create that fracture? That is balanced against the weight of the overlying firn or ice, so the snow, and once that reaches the fracture toughness of ice or the strength of ice to hold itself together, we can use those three things to calculate that initial depth of the crevasse. Why this is important is because when you have water in a crevasse, you add this term for the water pressure, which then can allow your crevasse to hydrofracture to the bed, and it will extend beyond that initial depth that just the conditions at the time of formation with no water involved created. So here in this area, because you don't have a supraglacial stream just running and dumping all this water into a crevasse like you do in the ablation area, if the initial depth of that crevasse is deep enough to intersect that firn aquifer water table, it can then start to access that water and then start the hydrofracturing process. And if the crevasse is too shallow, then it won't be able to access that water, and it shouldn't hydrofracture to the bed, and it should stay very narrow because it's going to be widening as it fractures deeper. So again, if crevasses can reach this firn aquifer upon their formation, then they can begin to hydrofracture. And so to implement this and calculate this for our area, I use a few different data sets. So first, we use the background stress field, which is derived from NASA's measure strain rate. So that's just satellite-derived strain of the ice. And then in the field, to constrain how heavy that overlying ice is, or well, here, firn or snow, we collected a series of snow pit measurements. So here you can see my GoPro attached to a ski pole. Now it's kind of melting and falling, showing my two colleagues, Colin Meyer and Ian McDowell, digging a snow pit here, and then they're measuring the snow density and recording that with depth. So we use those observations to constrain how heavy that ice is over and snow is over the firn aquifer to equate it to the fracture toughness of ice. And then we use those two to calculate initial crevasse depth, and then we can compare it to these Operation Ice Bridge derived water table depths. So here we're seeing again this same figure of our aerial view profile on the top of where those flight lines are and where we're actually measuring the firn aquifer water table. The orange dots show, just for reference, the location of our GPS stations that I talked about earlier. And then these blue triangles indicate the locations in which a series of direct observations of the firn aquifer depth were collected by Montgomery and others that went into the field in, was it 2015 and 2016? And they actually drilled through the surface of the all the surface firn until they hit liquid water. And those are indicated in the bottom by the black bars that show the surface elevation and the depth. And again, that blue shading corresponds to each year where the water table depth was beneath the ice surface. So next I will show the comparison with our calculations of initial crevasse depth. So we have the same panel up at the top. At the bottom, we have our water table depth plotted as meters below the ice surface. And this panel here is the magnitude of the surface stress. So that corresponds to just all of those colors, the shades of red that are overlying all of those those Operation Ice Bridge flight lines. And then here we have plotted just a profile view. So that dark blue line is ice surface elevation. The blue lines again correspond to the depth of the firn aquifer water table. The dashed blue line is an approximation of the depth of that firn aquifer. And the black eye looking things are those direct observations in 2015 and 16 of the firn aquifer depth. Panels C and D here show in orange our calculations of initial crevasse depth along our flight line. And there's a few things that stand out. So on the right-hand side in that purple shaded area, we have our main crevasse field. So that's where we're seeing that active opening of crevasses. And that location corresponds to the region where we have the deepest crevasse depths that occur at the time of their formation. So as a crevasse opens there, they are the deepest along this flight line. And that corresponds again well to where we're seeing the crevasse opening. Upstream of that, we're getting shallower crevasse depths and more sparse observations of the firn aquifer water table. But upstream from there, initial crevasse depth is decreasing largely with the magnitude of the stress on the ice. So to try and understand if the firn aquifer it can propagate inland in the future, we compare these initial crevasse depth observation with the firn aquifer water table and identify these three areas where the initial crevasse depth, again, this is theoretical crevasse depth in these areas, comes close to the firn aquifer water table height. And so 3 areas vulnerable to potential inland migration. To see if the process is currently underway, some of our observations here are from GPS stations that we installed on the ice sheet, and we actually detected a crevasse opening event at between these stations, Helheim 8 and 6 in blue. And that was quite unexpected because that is even further upstream than where we saw those narrow crevasses. Looking back at the satellite imagery, we see the presence of these whaleback dunes, which form when wind speeds are high and are very prevalent next to crevasses. So they form whenever high wind speeds, so over 50 kilometers an hour, are blowing snow, and this blowing snow hits a discontinuity in the snow surface, and then it starts to stick, and then it can create these whaleback dunes that are very long. Here's some examples of some whaleback dunes. So we have 3 types. The first type are ones where one crevasse has a lot of dunes. There's some crevasses with a single dune these are very wide crevasses. There are these narrow crevasses with a whaleback dune, and then there are some dunes that we couldn't see the crevasse for likely 2 reasons, which is one, the width of the crevasse is less than a half a meter, which is the resolution of satellite imagery. It got filled in after the fact, but doing some statistical analysis shows that the dunes with the narrow crevasses versus no visible crevasse are very similar in orientation and everything. So we were confident that they were indicative of an actual crevasse at some point. So we then went back and looked at worldview imagery to see what is the distribution of these dunes over time in our area. So we have 2015, and this is in purple. So I'm shading right now to show where we're seeing these whaleback dunes. So we have some expansion in 2020 that goes a little further inland, but we're concentrated until we have hit 2023, where we saw a significant 13-kilometer inland expansion of the presence of these dunes over a large area, indicating that there was some kind of change in dynamics or in conditions that expanded or changed the area where we're actually observing fracturing. This figure is just a reiteration of the same thing, just showing that in 2023, we had this big expansion of whaleback dune presence. So can the formation region of these crevasses change? The answer is yes, and it will depend on the level of the water table at the time of fracturing and the depth of that fracture. So you need those 2 things to align in time for the process to take place, but it does not appear that we're limited right now by the ability for crevasses to form in this area. Rather, it's the syncopation of those 2 processes together, which can spur the firn aquifer to drain at new locations and then potentially create a segmented firn aquifer. So just quickly some observations. So we did install some new GPS stations around some of these crevasses, and here is a picture of what another one of these crevasses looks like, and a picture into that crevasse on the big snow bridge that had already collapsed. And here's what it looks like inside these very long crevasses. I couldn't get deep enough into it to see or hear any of the water flow. But there wasn't a snow bridge, maybe we would have been able to get deeper to actually collect some of those observations. But we have received some of this data from our GPS stations that we installed around this crevasse that we suspect of hydrofracturing. And here is a plot showing this same crevasse and the widening over time. And that black line corresponds to the timing of the second photo. So you can also see visually the difference in the size as well as in our GPS observations. This data set revealed a few interesting features. First being that we had some cross-flow displacement. So here the ice is flowing to the left in the bottom photo, and we have GPS station motion that is actually indicative of mode 3 fracture. So instead of just widening like this, we're actually having some north to south displacement. So we're having some shearing of the crevasse over time that then recovers back into place, which is, and then here, let's see. So I have here the same photos again with the different stations labeled and color coded according to this figure. So here we have this across flow displacement, so perpendicular to the direction of flow. We have changes in the height, changes in the speed, and again, the crevasse width. And we're seeing some shearing over time that recovers. We see a step change in the height of the two observations and some changes in velocity as well, which is indicating that we have these 4 phases of crevasse dynamic motion. And the velocity change is very interesting because we're having higher summertime velocities that then decrease over time. Altogether, this indicates that fracturing is very dynamic and that we're having complex crevasse opening that is has some longevity after the time the crevasse initially formed. So if you recall the earlier satellite images I showed where we first saw this crevasse in 2022, this data is from 2023. So we're having actually quite a long dynamic profile here. And we still had growth in 2024 as well. I was going to speak quickly about some work on modeling crevasse propagation, but I don't think I have time, so I'm going to skip ahead. Maybe I can talk about this, but I was working with some collaborators at Vanderbilt University and Oxford University, and we were doing some modeling of these rapid supraglacial lake drainages and showing that you need to consider the viscosity of the ice in your measurements in order to accurately represent how the ice is flexing and how that water is reaching the bed in these really rapid drainages. So an interesting thing here is that when a firn aquifer is draining, we're talking about length scales of time over months, right? We're talking about, more than half a year. Whereas whenever rapid supraglacial lake or supraglacial lakes drain rapidly, or even whenever a stream is flowing into a crevasse to fracture that to the bed, these processes are happening over the timescales of hours, which is highlighted by this minute bar. So we're getting much larger volumes of water to the bed much quicker in time. And even over these short timescales, this viscoelastic property of the deformation of the ice is important, and that's the key takeaway there. And then I want to highlight some work that I've been doing in the development of cryocommunity.org, which is aspiring to be a DEI or diversity, equity, and inclusion hub for the cryospheric science community. And one of our new initiatives is creating virtual ice community engagement squads. So to connect researchers at different institutions, particularly grad students, where there aren't large research communities and grad students or research groups may be siloed, to give them networking, connections, and career building and cohort building and mentoring resources that they may not have readily available to them, because thankfully glaciology research is growing and we're seeing glaciologists pop up at many more institutions than there were 10 years ago or 20 years ago. So it is a good problem to have in that sense, but just to try to create a lot of these resources and bring people together. Thank you.
Okay, thank you, Jessica, for that great presentation. Let's see here. So I think we're up to question and have time for question and answers. So we'll open it up. As a reminder, if you're joining by video, you may use the raise hand feature to ask your question. If you're joining by phone, you can raise your hand by pressing *9 and unmute yourself by pressing *6. If you need, Jessica has also offered to be available for another 10 to 15 minutes after the top of the hour. I did not see any questions come up in the chat, so hopefully people will raise their hand and ask you live. So, okay, so we have Mike, go ahead.
So thank you. That was really interesting. I have a couple of questions. One, when you were showing the sea level rise rate in the early part of your presentation, did that include shifting of the ice and ice stream movement and calving, or was that all surface melting contribution?
Oh, great question, Mike. Thanks for asking one. So that contribution was total mass loss from the Greenland ice sheet. So that data was from the GRAY satellite, which is taking gravity measurements from the Earth and looking at the change in gravity and then backing out mass loss from there. So it's those two processes combined.
So is this calving? I guess what I'm curious about in the future is what is going to be the biggest contribution for it? Is it going to be from melting the ice, or is it going to be from ice moving and calving into the ocean?
So for the last while, I guess, previous to quite recently, a few years ago, calving has been the #1 mass loss mechanism of Greenland, especially because there are a handful of very fast moving glaciers that just put out such a large number of icebergs. And there's just so many peripheral glaciers. But a few years ago, I don't remember which year it switched over, but now melting and runoff has recently surpassed the calving and ice dynamics. And I would expect melting to continue to dominate ice dynamic mass loss as they presumably both increase. We've just been seeing so very dramatic changes in runoff. For example, there was a rain event, so liquid rain and melting at Summit Station, which is located in the middle of the ice sheet. So it was that 2022. And that rain event that happened in 2022, it was the first time rainfall had ever been recorded in all of our ice core history ever in the middle of the ice sheet there, where they didn't even have a rain gauge because it had never in history rained. But now we're even seeing rain events that are happening in the middle of the ice sheet and melting expanding further and further inland. So moving forward, it should be melting.
Thanks.
Thank you for the question.
Okay, before I get to Tamara, there was a question from Ursula in the chat. I am curious whether you were able to identify the PFA drainage in conjunction with an acceleration of ice velocity, or if the signal was obscured by seasonal velocity dynamics. Second, have you looked at other areas in Greenland and seen similar shifts of crevasses occurring more inland?
Oh, great questions. Thank you. To address the first one, what is interesting is that we do see velocity change, which we did not necessarily expect. Right now, I've been doing analyses to try to basically disprove other potential causes for the changes in velocity that we're seeing, such as the ice affecting over a bedrock bump and us getting some differences in motion, or is it the vertical component of motion and how that lines up, to see what other dynamics it could be there. But that's something that I'm actively working on and trying to see if we can make a big case for there being this active drainage network underneath the ice sheet at the time. But from the data that we have right now, I'm very excited about it, and there are potential implications or direct observations there of that drainage. But by the time that we instrumented the crevasse, and we did a lot of this modeling work after we had, there should have already been that hydraulic connection that existed. So we weren't able to capture that initial connection of the crevasse. We missed that by, I think, about a year. But hopefully we can attribute some of the changes to a persistent hydraulic connection. So it's a little different. The second question is, did I look at other areas and see if there is a change in location of crevasses? I have not looked extensively at other areas, but more corroborating evidence for the potential for these things to change is that we do observe some what I called segmented firn aquifers. And what that is a crevasse. There's firn aquifer from up glacier at the end of it. Then we see the crevasse field, which I showed. But there are some instances of smaller firn aquifers and then more crevasses that are downstream of where we were focusing on. And theoretically, if we were to have more crevasses forming even further up glacier than we see today, that firn aquifer may segment. So that presence may be indicative of this. And we did see just crevasse growth in a new area in 2024. So there is some evidence, but I haven't looked systematically at other areas yet, but it's definitely something I want to check out. Thanks for the question.
Okay, Tamara, we'll go to you.
Yes, thank you for your talk. I really enjoyed it. I was wondering, so you talked about the water level or the depth of the aquifer, and how it varied in space and in time. And I was wondering if you know something about the aquifer thickness and how that affects like whether hydrofracturing occurs, or like how much total water is accessing the crevasse.
Yeah, so the firn aquifer can range from maybe 10 to 20 meters thick, plus or minus maybe 5 over time. There's only been a handful of direct observations of the actual aquifer thickness. A graduate student from the University of Buffalo, her name is Courtney Schaefer. She brought out onto the ice this like seismoelectric experiment where basically you create an active seismic source and you're supposed to be able to use the signal to see the surface and the depth. Because one limitation of the Operation Ice Bridge is that we just have that the surface elevation, not the bottom of the aquifer. So there's a few point measurements, and I think we might need more to really constrain things, but presumably there should be a difference in the flux unless there's a change in the speed that travels through thinner areas of the firn aquifer. But I think maybe some modeling could help to show how that might affect actually like the flux of water going into a crevasse. But right now it's so unconstrained that we kind of don't know the flux going into these things, regardless of the thick, even when they're very thick. So I think we might need some more observations to parse out that relationship, but it's definitely something interesting.
Thank you.
Okay. I'll have you respond to this one question in the chat, and then we'll do a soft close. And anybody that I didn't get to or has additional questions, like I said at the beginning, Jessica will stay on past the end of the hour, which is coming up. So this message from, or this question from AC Conover is, in the map of firn aquifer sites, was the lack of sites in the Northeast Greenland a reflection of data scarcity, or has it been surveyed as well?
As you get away from main outlet glaciers, there is some artifacts of data scarcity, but Petermann Glacier is up there, and I think, if I'm recalling correctly, Petermann is a very large glacier in the Northeast and is surveyed quite a bit. So there definitely were flight lines consistently all over the periphery of Greenland, and I think that is mostly an effect of the magnitude of melting and then the subsequent snowfall. So for example, why we see the concentration mostly in the southeast is because we do have a lot of melting coming in from these different atmospheric circulation patterns, and then also a lot of snowfall and moisture coming from the ocean in there, like up from Greenland or Iceland, excuse me. So it's really those weather patterns that are causing some of these observations. So it's not necessarily the data scarcity, but I'm sure things could have been missed.
Okay. Thank you so much for answering those. I think at the moment, because we're coming up on top of the hour, we'll do a quick close. And for those of you that want to continue discussion or that posted questions, Jessica will be here for another 10 to 15 minutes, and we can keep adding your questions in the chat, and I'll have her respond to those so that they get recorded. For those of you leaving now, we want to thank you for joining us today. On behalf of ARCUS, we want to thank you, give a special thanks to Dr. Mejia for her time and this excellent presentation. ARCUS wanted to share with you also one upcoming in-person event that is sponsored by ARCUS. It is the 2025 Alaska Outdoor and Environmental Education Symposium called Strength and Community. It will be held here in Anchorage, Alaska, February 21st, 2025. Again, that's an in-person meeting. So if you know of anybody that's in Alaska that would like to attend, please share this with them. This is a current call for session proposals. The proposals are due this coming, not coming Sunday, but soon, Sunday, December 15th. And we also will post in the link, I think actually Stacy has already done it, the links to submitting proposals and also to register for the symposium. We are currently working to improve our seminar series, as well as looking for suggestions for future seminar topics and speakers. Please take a minute or two to complete our short survey. There's a QR code on the screen to do so, and a link in the chat. And again, thank you for joining us today. This will conclude this part of the webinar. Feel free to stay on if you want to hear responses to those questions that were posted in chat. A recording will be posted online and sent out by email to everybody that joined. So thank you so much and have a great day. And with that, Jessica, I will go back to the questions that got posted while you were talking. So from John Dempsey, he wanted to know, are you monitoring the opening and loading parallel to the crevasses?
I'm not sure what you mean by loading. We were only measuring the widening of the crevasse. I think now that we've seen some of the other complex ice motion, and maybe we would have wanted to have very small strain diamonds in the area to really monitor the way that the ice is moving around the crevasses. But again, that's challenging since new crevasses keep opening and we keep unfortunately losing our GPS stations that get buried in snow. But that's definitely something we would love to
So,
record better.
so recent fracture research has sort of turned fracture mechanics on its head. It's like we have to start again. What it's showing is that the crack parallel loads are much more important than anybody had anticipated. And I just wonder if you can work it into your measurements, why some crevasses are active and why some are not. You never know. The loading parallel to the crevasse could be a factor.
Yes, and that may also explain a lot of that complex ice motion that I was showing with that, transverse to flow. So that
Yeah.
north-south motion was, parallel to the strike of the crevasse. And we do
Really?
see what actually looks like rifting going on that we don't really have a good explanation for. I think in the design of the experiment, we were really trying to align with those Operation Icebridge flight lines of the firn aquifer, which were very narrowly constrained. But if I could go back in time and change the way that we installed those GPS stations, I think I would definitely want to explore some of that parallel loading that you're discussing and
Yep.
finding a way to. We were trying to put out some very small GPS units. A graduate student at Dartmouth is creating something called an ogre, which is this big. They're little tiny ones that are not like my giant 300-pound GPS stations, and we're testing them out on the ice right now. So hopefully they survive. And if so, I think that will provide some opportunities to get a denser array of GPS stations out there to actually explore these things, which would be very exciting.
Yep. Very good.
Okay, I don't know if Gabriel's still here, but Gabriella. Anyway, there was a question. Was it possible to see if the size of the crevasse has a relationship with their orientation and also with the detachment of the layers of the glacier, such as avalanches or icebergs in the ice sheet?
So in this area, we don't really have ice avalanches. Those are typically snow on the side of mountains. And where the area is pretty flat, like in the photos that I showed. As for the orientation with iceberg calving, very far downstream from where we are, 40 kilometers is where the terminus is, and we're seeing the icebergs calving into the ocean. And the damage of the ice as it gets all the way down there, and every crevasse that has formed and healed and cracked the ice into a million pieces and kind of pushed it back together, so it's kind of a mess. That definitely does change or affect the shape of those icebergs that are calving into the ocean. And some people are doing some really interesting modeling, like at Georgia Tech and at University of Chicago, of some damage mechanics. So you're kind of modeling how broken up is the ice and modeling the calving from there and the icebergs, which is really interesting.
Yeah, so this is all very fascinating. We have a question for Mike McCracken. I don't think he's still on, but one of the proposed climate intervention approaches is clearing of winter cirrus in order to allow more wintertime loss of IR to space. If this could be done, would the increased wintertime heat loss chill the ice sheet enough to slow the rate of loss of mass in the warm season and so slow the rate of sea level rise?
Slow the rate of mass loss in the warm season. With the increased wintertime heat loss, chill the ice sheet enough to slow. So, not in the case of a firn aquifer. So if it gets negative 60 degrees in our area in the winter and we have that snow layer that's having this insulating effect to keep a firn aquifer liquid, if we warm, we're not going to create wintertime melting in the area to contribute to it, to the growth of the firn aquifer, which we don't see now, and it shouldn't affect the presence of firn aquifers. So I don't see how that would affect the firn aquifer system. Overall mass loss of the ice sheet, I don't think changing the wintertime heat balance by a few degrees would, I mean, if it is colder in the summer, then that would help, but you would need to decrease these giant melt events that we're seeing across the ice sheet and not continue to break melt records for Greenland every year, it seems.
So one of the reasons I posed that is because it's kind of interesting that if you go back to 6,000, 7,000 BP, there was the Milankovitch orbital parameters were such that the northern hemisphere was getting a lot more, 6 or 7% more solar radiation in the summer, so a fair amount more energy and could lead to a lot of melting. And yet the ice sheet seemed to withstand that. I mean, there'd been a drop. Well, sea level at least was stable, I guess I should say. And it's just kind of interesting to wonder how that worked. Back then, of course, the CO2 concentration was lower, and so that was allowing more IR loss. Now you have a higher CO2 concentrations, you're getting more back radiation from that, but would clearing the cirrus reduce it and sort of try and emulate what happened during the early Holocene? So that's the reason for the question.
Yeah, I'm not too sure about that then, but I don't know.
I mean, you also have those, the passages down into the ice that could bring heat up as well. So the surface is insulated with snow, but I guess there could be heat that comes out from down below as well. So just an interesting thing to think about, perhaps.
Yeah, and the presence of just liquid water in the crevasse. So I didn't get too into the details of the crevasse model that I was running, but we do calculate, in addition to the water coming into the crevasse and it propagating and fracturing, we do keep track and calculate any refreezing of the crevasse walls, which is then taking into account the heat diffusion into the ice in the firn from that water, from the latent heat of freezing and going into that. So Kristen Poinar, she has done some modeling work of the same process and shown that trying to calculate and define just the effect of having not all the way hydrofractured crevasses that are just storing liquid water within the ice sheet, and showing that that will eventually warm the temperature of the ice.
Thanks.
Which is interesting.
Okay, this is a question from Naomi Short, and it looks like they are online. Firn aquifers show up very clearly in satellite radar imagery. Do you use this imagery to detect the presence and extent of firn aquifers?
I don't personally, but a lot of people do, which is really interesting. Yeah, my work has mostly been focused on kind of like this one area, but be interesting to see, especially to supplement the Operation Ice Bridge record, which that campaign ended in 2018 was the last flights in our area, which is very unfortunate because they collected such amazing data all over Greenland that we're still, writing papers about new things that we're finding in that data today. So that would be a great thing to try and see in this area to supplement that, because we have, just from those Operation Ice Bridge observations, have detected the expansion inland of the firn aquifer over time. So yeah, that would be something interesting to look into.
Okay, Andy Bliss, who I think is still on. So Andy's is asking, I'm curious if you could comment on how crevasse and drainage patterns at the Helheim compared to Alaska tidewater glaciers, e.g. Yahtzee.
So on Helheim is actually probably one of the much bigger but more similar glaciers to an Alaskan or alpine glacier. So Yahtzee has a big ice fall and slides, I mean, much faster or very fast, and parts of Helheim are extremely fast as well. So both of them have these big ice falls, and the ice, when it's calving, is extremely damaged. So that is, you know, a very staunch similarity. The main, I think, difference in the crevasse patterns are that in alpine glaciers such as Yahtzee, or really most of them in Alaska, you have all of this ice flow between the mountain walls that is exerting a very significant shear drag laterally and creating a lot of that side fracturing. And in Greenland, we're getting a lot of our differences in fracture patterns from the bed. So underneath, where we're kind of able to just see those fracture patterns that are resulting from it. And the ice is a lot thicker. So there are a lot of similarities, especially as you get closer to the ocean in Greenland on the glaciers. Then there are very much similarities. It's just a lot more ice that's coming through.
Okay. And I think that's it. If anybody is still here with us, which actually there's a number of you, you feel free to just open up your mic and ask a question if that's what you need. Otherwise, thank you, Jessica.